So the following function is given to us, okay, and we're told that this is the rate at which Laura's bicycle or motorcycle depreciates per amount of time. So the unit associated with the numbers that this function computes is the dollar amount that Laura's bicycle depreciates by per some kind of time frame, in this case here. Okay. So it always helps to actually evaluate the function at some time to develop a more intuitive, understanding of what the function is actually giving you. Okay, so let's see what this function gives us when we plug in 4 years into it. So after 4 years, okay, the function gives us 900 and let's see, minus $919.70 per year. Okay, so what this means is that after 4 years, right after her motorcycle turns 4 years old, okay, her motorcycle will be depreciating at $919.70 per year. Okay. Let's see what happens after 8 years, okay, and see whether this rate of depreciation actually increases or not. Okay. So 2,500 multiplied by e to the power of -2 gives us -$338.34 per year. Okay. So after her motorcycle turns 8 years old, we see that the rate of depreciation is actually smaller than after 4 years old. Okay. So as you could imagine, this pattern persists. The older the motorcycle gets, the slower the rate of depreciation. Okay. Now, the question itself is asking, at what time does Laura's motorcycle depreciate in value the fastest? Okay. So at what time is v prime of x, okay, or the rate of change of v of t, the fastest? Okay. And to solve this question, what we need to do is we need the rate of change of the depreciation rate given by v prime of t. Or mathematically, we need the double derivative or the second derivative of v of t. So I'm going to differentiate that. That's an exponential function, so it should be fairly easy to differentiate using the chain rule. Okay. And simplify it algebraically, and we get 625 to the power times e to the power of -t over 4. And just so that we can develop a better intuition, I'm going to rearrange that and put e to the power of t divided by 4 in the denominator. Okay. So what does the denominator look like? Okay, if I were to graph that function, that graph looks like this, right? It's an exponential function. Okay. And because our independent variable t is time, t has to be a number greater than or equal to 0. Okay, you can't have negative time. Okay. So, assuming that t is greater than 0, okay, we see that the value of e to the power of t divided by 4 is smallest at time 0. Okay. As t gets bigger and bigger, this denominator gets bigger and bigger. And as the denominator gets bigger and bigger, the second derivative becomes smaller and smaller. Okay, so this particular value, all of this, really is at its maximum when t is equal to 0. Okay, so at time 0, okay, the denominator will simply be e to the power of 0, which is equal to 1. And time 0, the change in the depreciation rate will be $625 per year per year. Okay. So when does Laura's motorcycle depreciate in value the fastest? It depreciates in value the fastest, okay, right now at time 0. And that reasoning is actually consistent with the intuition that we had developed here. Okay, you see how the depreciation rate is higher at an earlier time, and the depreciation rate will get smaller and smaller as time elapses. Okay, so v prime of 0 would actually be a bigger number. Okay, the motorcycle will depreciate at a higher rate, okay, than at a later time.